Computer systems and networks is the big idea of the AP exam that focuses mostly on the internet and how networked communicate. Computer systems and networks is the big idea of the AP exam that focuses in on the internet and how multiple computers can work together to solve the same problems. This is only going to be about 11 to 15% of the actual test, but there's a lot of small details that might show up, so it's important to understand all the different protocols of the internet and the different ways work can be distributed across a network to make sure a job gets done. The guiding question for this unit is how can computers reliably communicate with each other, and the word reliable is key here. It's not just how computers talk to each other, but how they can do so in a way that is fault tolerant, and to make sure that problems don't just spring up every time you try sending data to someone else. So a couple key terms you need to know going into this is that when we talk about a computer network, this is a group of interconnected devices capable of sending and receiving data from each other. This doesn't mean they're all operating the same way at the same time, it just means they can communicate with each other. When they try to communicate with each other, the data finds a path between these computers through a process called routing, which you can hopefully see comes from the word route. And when we talk about routing, we also want to talk about the bandwidth of a network. It's how many bits, the maximum rate of bits that can be transferred between computers at any given time. It's expressed as a rate, so bits per second. There's also going to be other issues that come up, things like latency, which will be the delay, how much time it takes for this information to travel. And as you develop computer network architecture, hopefully you're acknowledging these problems and finding ways around it. So let's talk about the internet. When we say the internet, what it means is it's actually just this set of standardized open communication protocols that all the computers that wish to participate on the internet have to follow in order to access and understand the information being shared. Now, these protocols are open, so any device can learn how to use it as long as they're programmed to do so, and can become part of this larger network of devices. These protocols were designed to be scalable. They were designed so that you could have it work between 10 computers or tens of thousands of computers. In fact, the way most of these protocols were written, they actually get stronger when there's a larger web, when there's more computers that could help share the load of all the data that's trying to be transferred. The way all these computers can communicate is through packets. They take chunks of data and send them through what we call data streams to each other. This is important to distinguish from the World Wide Web, or sometimes the internet with a capital I. The World Wide Web, the internet you're probably used to using in browsers like Google Chrome and Firefox and things like that, that's a specific set of files and web pages that communicate via Hypertext Transfer Protocol, HTTP. And those are transmitted as part of the internet. But the internet is more than that. It can send files that aren't necessarily part of the World Wide Web. The protocols that guide the internet start with packets. So any file you wish to receive, say this video, is cut up into small packets, and all of those packets are transmitted, just like if you ordered a really, really large package. Maybe you ordered a treadmill, and it's coming in multiple parts in multiple boxes. Just like real packages, these packages might arrive in the wrong order. You might get package 1, then 3, then 2, and sometimes package 2 might not arrive at all. And so protocols need to be put in place to make sure that the data can be transmitted reliably and accurately. First, we start with the Internet Protocol, IP. This is just the addressing system. We are currently using IPv4, but we're switching to IPv6, which is just a way to use bits to denote the address and location of a computing device. Routers take these IP addresses like labels, like address labels on a package. So when they receive a package, they'll look at the IP address labeled on it and use this to figure out where to send it next. Routers do this dynamically. Packets don't show up with a path. Packets just show up with a destination. And each router independently decides the best way it should reach its destination. This is important in case there's sudden outages or traffic along different locations that might not have been issues when the package was first sent. It allows the internet to adapt to those problems. Other protocols you'll run into are Transmission Control Protocol, TCP. This is basically just labeling these packets 1 of 5, 2 of 5, 3 of 5, 4 of 5, 5 of 5, so that when a computer receives it, 1, it knows to put it in order, and 2, it can identify if anything's missing. This might not be the best for things like streaming videos or playing games, though. So we also have the User Datagram Protocol. That way you can stream media, but it's okay if maybe a frame or two gets lost along the way. The rest of it will get to you efficiently. There are a ton of other protocols that work with the internet. For example, DNS, the domain name system, that lets you put in URLs instead of having to type in IP addresses to find web pages. One of the most amazing things about the internet, though, is its fault tolerance gained via redundancy. Fault tolerance is a way of saying, yes, we know there will be problems that come up with our system. They live in the real world and problems happen. But our system can address those and function even with these problems happening. With the internet, we have a huge network of devices and routers that are interconnected. So even if a single device fails or a ton of devices fail, there's paths around it where data can be transferred around the problem spots and still reach their destination. This might not be the most efficient thing in terms of hardware or absolute financial costs, but it more than makes up for it by making sure that there's a consistent connection on the internet. The entire internet just can't go down because one person's updating the computer. The last thing with these computer networks is that they can work together to solve bigger problems. Traditionally, a simple problem could be solved sequentially using sequential computing. One operation is solved one at a time, one after the other until the problem is done. But parallel computing lets you divide up those problems between different sources. Maybe it's different cores on a processor or different devices altogether. And if there's two sets of those operations that could be solved simultaneously, they get to work on those at the same time. We could distribute that amongst even more devices to run things even faster. A parallel solution is now going to take as long as any sequential steps that need to happen first. Maybe you need some value to do the future calculations all at the same time. Plus the slowest segment. Even if other parallel segments can run faster, the slowest one's still going to be a limiting factor here. We can calculate this actual speedup by taking the purely sequential time, if we only ran things one at a time, and dividing it by the time the new parallel solution takes. And that'll give you some number that will be greater than 1 that tells you the speedup. Parallel and distributed computing helps scale because they can help you share processing power, and the more processing power you have, the better you can do. And you also have more places to store data. But at the same time, there's still going to be these limiting sequential portions to processing. Take, for example, a long list of numbers you want to multiply by some coefficient. You can have different computers multiply all those different numbers for you, but you still need to figure out that coefficient first.